So, good evening, everyone. Thank you all very much for coming along. My name's Lewis, and the event that I hope you've come along to tonight is all about the apocalypse, the existential hazards that might collapse our society, and what we might be able to do to prevent those or how to rebuild afterwards. This is our panel for tonight, and I think if we start with Vinay. Vinay, what's your name? And then we'll move my way and introduce ourselves in turn.
I'm Vinay Gupta. I used to do a lot of worst-case scenario planning and built a shelter called the Hexayurt, which is quite widely used. And now I'm part of a venture capital firm called Hexayurt.Capital.
Good evening, everybody. I'm Hugh Lewis. I'm from the University of Southampton. I do a lot of research into asteroid impacts and work for the UK Space Agency and represent them at an organisation called the Space Mission Planning Advisory Group.
My name is Rosalind Eggo. I'm a researcher at the London School of Hygiene and Tropical Medicine, and I study the dynamics of infectious diseases.
And my name's Lewis Dartnell. I'm a professor at the University of Westminster, and my research is all about astrobiology and how we look for life on other planets. But what I'll be talking to you about tonight is how we could reboot civilization if these guys screw up and the end does come. The format for tonight, it will be that each of us will talk for 10 minutes, and we'll have a wee bit of a chat amongst ourselves, and then I'm very, very keen to save lots of time for all of you to ask questions of our audience as we explore these ideas of the apocalypse and what could be done to make sure it never happens. But Vinay, you are up first. Have you got your clicker for the slides?
I'm not using slides.
What?
No.
Take it away then.
Right, I cannot quite see that clock, so you'll have to excuse me keeping my phone visible. So basically, the large-scale threats could be grouped into three simple categories. What you might refer to as physical threats. So this is asteroids, space weather, this kind of stuff. Second category you could think of as being natural threats. So this is largely infectious disease, maybe a few other things. And then the third category is man-made threats. And man-made threats are by far the worst of the three categories in terms of likelihood. So the kind of threats that you see in the first category are basically threats from the sun, so things like solar flares or Carrington events, threats from asteroids, and then there's a kind of third category of sort of unknown unknowns, gamma ray bursts or other weird, huge cosmic phenomena that could crisp us. The biological threats, we have things like the World Health Organization putting up very, very strong defenses to things like pandemic flu, but there are always the unknown unknowns. Where I focus most of my time and attention is actually on the man-made threats. And this is an era that starts with the nuclear bomb. And once you have the nuclear age beginning, the primary driver for the man-made threats is actually weapons research. So you go through the nuclear bomb, we build enough nuclear bombs to annihilate the world. Pretty much the only people that take this seriously are the Campaign for Nuclear Disarmament, who are largely publicly regarded as a laughingstock, although history has shown that they're right about basically everything. Right on the back of this then comes the golden era of biological weapons research, which is kind of the 60s to the 80s. And by the end of that period, most of the players have got buckets full of everybody on Earth dies in like 4 or 5 months. And all of this stuff is super highly classified, and occasionally you'll get like a Russian defector who's like, you have no idea what we have in the freezers, and the Americans are like, no, we totally know. I don't recommend reading about that stuff unless you want permanent nightmares. The next set of threats is even worse, and this is, sorry, you did come. So the next set of threats is the really hard stuff, which is genetic engineering of weapons. So there's a bunch of work on things like genetically engineered smallpox, and the animal models produce organisms which are simply 100% of mice die. Don't even ask what people are doing with this in the classified world. I don't know, nobody knows, but you can do the math. Beyond biological, there is also the possibility of nanotechnology and synthetic biology producing organisms that have completely new kinds of properties. or aren't really organisms but replicate in the same way that organisms do. So they're a bit like computer viruses or little robots that make copies of themselves, imitations of life but with none of the kind of baggage. And you can imagine a kind of accident where you've got a pair of molecular shears which are designed to chop up organic matter like oil into little pieces so you can, say, make methane. And then this stuff discovers that, actually all animals are made out of oil, and it just chops up all the oil bits inside of humans. And suddenly you have your kind of massive replicating plague. This stuff is not today's threat, but the odds are that synthetic biology and nanotech are going to be used on an enormous scale once they're available, because they will give us the ability to program matter. But the problem is that once you can program matter, if you make a mistake, it will be like a computer virus in the real world. And this is a threat they talk about as grey goo. Let me just check how I'm doing for time. Oh, splendid. Now, then we get the kind of large macro threat, which goes under the general kind of numinous title of artificial intelligence. Now, I am not given to be paranoid about artificial intelligence. This is one of the few areas where I am anything less than alarmist, because I have a fairly strong feeling that the nature of intelligence doesn't permit superintelligence to exist. I think that intelligence is more like the sensitivity of photographic film, and when you get something which is overexposed, you just get kind of a useless whiteness. So I think the idea of superintelligence is basically the idea of having like 50 million ISO film and all that you will get is whiteness. So what is the whiteness that we would get in this kind of scenario? Has anybody noticed that really intelligent people tend to have one or two beliefs that are completely barking mad? Right? So once you've got sufficient processing power to be able to take huge data sets and arbitrarily rearrange them, you can more or less justify anything to yourself if you put your mind to it. But also you can spot patterns which aren't there, and the patterns are so sophisticated that almost nobody can disprove your pattern. So I think there's this tendency that very smart people wind up with a couple of crank beliefs, and the smarter they are, the more of these things they get on average, kind of on a bell curve. So my feeling is that the threat is not super intelligent AI, which would be bad, but merely terribly intelligent AI, which is also crazy. And that kind of world where you wind up with trading algorithms for things like the world's food system run by artificial intelligences, which also believe very hard to debug things which aren't true, gets into this domain where you have hugely powerful, hard to control irrational actors crashing around at 50 million times the speed at which a human being can react. So you get things like the flash crashes caused by automated trading algorithms, but now the things are artificially intelligent. So it's not that I think that you can hold out hope for a kind of Bond villain intelligence which runs the entire world according to some great grand design, but more a bunch of kind of crazy, insane internet gods bashing up against each other trying to make money for some set of corporations, which is not nearly such a big existential threat, but could still make life reassuringly miserable. Now, let me say very briefly something about what the resistance to these threats is. You could look at the entire medical system as being the primary line of defense against the biological threats. Whether this stuff is natural, whether it's artificial, whether it's genetic, whether it's bioweapons, the first thing that will stop this is epidemiology and medicine. And this comes down to people in masks dealing with cases. The second kind of wave of this sort of stuff is the defense lines which are maintained by the state. So you've got all kinds of mitigation, remediation, apocalypse planning stuff done by governments. Most of that stuff is classified. You sort of think maybe they have it under control in the classified world, but they certainly don't have it under control in the civil contingencies world. For example, the pandemic flu planning that was done for the UK by, I can't remember what the name of the body was, but it was an official body doing the planning for London, had the maximum scenario with about 2% mortality at a point where the current organism of concern was showing up as being about 70% fatal. And nobody expects an organism at that level of lethality to become infectious. The lethality typically drops extremely rapidly once the diseases go pandemic. But still 2% was an incredibly artificially low threshold because it was the highest threshold at which you could imagine normal life continuing. And they didn't want to scare people. And this is the common thread all the way through this work, is that people don't want to be scared. But if we're going to organise collective response to these threats, people need to be scared enough to act, or they need to be motivated to act in other ways. The last thing I want to talk about very briefly is climate. So a lot of people act as if climate is an apocalyptic threat, but in most scenarios, most human beings survive most of the climate outcomes. You could imagine very large-scale famines, which would certainly be disasters, but it's a disaster on a different scale from some kind of, nanotechnology, genetic snippers coming along and going out of control. But it is the apocalypse that is closest to us, right? That is the ongoing, rolling thing that we're all sitting in the middle of. And if you get a sense of the kind of general ineffectiveness of response to climate change, the hardship of getting society organized to act, that is very typical of what's happening through the rest of this space. You get isolated pockets of resistance, largely funded by billionaires, and the rest of it is the slow grinding machinery of society trying to do well at dealing with problems which are low down the list of people's immediate urgent priorities, and we just kind of muddle along. But we made it this far, and the hope is that we will continue to. Thanks.
Excellent. Thank you, Vinay. And now to you, Hugh.
Thank you very much. I'm going to use some slides up here just to help me with my talk. With respect to asteroid impacts, I have some good news and I have some bad news. I'm going to start with the bad news and finish with the good news, and hopefully leave you feeling a bit more optimistic about the situation. Asteroids, okay, there are a lot of asteroids in the solar system. We're currently aware of about 600,000 asteroids, so we know where they are, what they're doing. And of that set of objects, there are some that get close to the Earth. And at the moment, using the catalogue that we've generated at the moment, there are just over 16,000 of these objects that get close to the Earth. How close to the Earth? Well, we're talking several million kilometers. That's where we start to get a bit sweaty and worried in solar system terms. But we know that these things are a threat because we have found impact craters on the Earth. We can just look at the moon in the sky and we can see hundreds and hundreds of craters on the moon. So we know that they are a real threat to the Earth. Of that population of asteroids that could hit the Earth, most of them are actually relatively small. So, you might think, that's okay, we don't need to worry about those. But a little later on, I'll show you why we do need to worry about those particular ones. On this chart, the ones in red here are bigger than 1 kilometer across. So 1 kilometer is pretty big, coming at us maybe about 40,000, 50,000 kilometers an hour. That would do an awful lot of damage to the Earth. And again, we know the kind of damage that can be caused when we look at objects this size because mass extinctions have occurred in history. Certainly the dinosaurs might have something to say about that as well. So in terms of the frequency that these objects tend to strike the Earth, as I've said, the smaller objects, maybe a few meters across, are really, really numerous in the solar system. And they hit the Earth very, very frequently. So we will expect to see small impacts into the Earth's atmosphere probably every day. Okay, and we'd see those as shooting stars, as an example. As we go up in size, then the interval between the impacts is going to increase. Okay, so we don't necessarily need to worry about the kind of extinction level event so much, because maybe that happens once a million years, once every 10 million years. That is the type of event that would probably wipe out all life on the planet, thanks to the catastrophic effects that would take place immediately after the impact, but also then the very long-term effects, throwing all the dust and material into the atmosphere so it blocks out the sun. That tends to cause problems for life on the planet. So really, what I'm worried about are the things that are smaller than that, the things that happen every year, happen every 10 years. So the sizes we're talking about, maybe the size of this lecture theatre, maybe once a year would strike the Earth. So what we've done at Southampton is did a bit of research. We looked at all the potential asteroids that could hit the Earth, and we've figured out where they could hit. So this is actually a small subset of the asteroids that could hit the Earth. So these are the ones that NASA and European Space Agency say have some probability of hitting the Earth, and we plotted where they could hit. And the thing about this map, really, that's the most important thing, is that they could hit anywhere. Okay? Everybody is at risk from an asteroid impact. It's not exclusive to any particular region on the planet. In terms of the effects, I've got a picture here of one of the effects, which I'm going to talk a little bit about. This is an airburst. But anybody know what else would happen if an asteroid were hit the Earth's surface? Yeah, okay, so if we have an impact into the ocean, we can generate a tsunami. Okay, so and again, we've all have experience watching the news, seeing things like the 2004 Boxing Day tsunami in Indonesia and around the world. The Japanese event, which took place in 2011. So tsunami is another obvious one. I've mentioned them already, craters. Okay, these things impact the Earth's surface, and they basically excavate a huge amount of material. Other effects, seismic shaking, so you get earthquakes from these things as well. That when they impact, all the energy that they have, and it's a huge amount of energy, okay, they're traveling very quickly, the huge amount of mass, a lot of that gets converted into heat. So again, you get thermal radiation effects from that. You'll get huge winds as well, both due to the explosion that could happen, and also due to the overpressure and that wave that expands outwards. And so you're talking about wind speeds relatively close to the impact site, maybe a couple of thousand miles an hour. Compare that to hurricane kind of force winds and tornadoes, and it's a whole different ballgame, really. So I'm going to talk about airbursts, and the reason I want to talk about airbursts because we've discovered that these type of events are actually potentially the ones that lead to the most casualties. Okay? Even if the asteroid doesn't make it down to the Earth's surface, this type of event can be really, really problematic. And we saw that in Chelyabinsk in Russia just a few years ago. So this was dash cam footage of an asteroid coming in. Again, this asteroid about the size of this lecture theatre. Okay, coming in. Very, very bright fireball. Looks amazing. Left this lovely trail in the sky. And that actually is really important in terms of what happened, because people saw this very, very bright light. So they stopped and looked. They went to windows to have a look out. Saw this cloud trail, very, very unique, because that's 90 kilometers up 30 kilometers up and 90 kilometers long, that cloud trail. So it's really quite a big feature. And as you can see, lots of people with videos were filming this after the event. So this is maybe a couple of minutes after the bright flash. You see the fireball. I'm going to play this video. It's relatively brief, and things happen quite quickly. And depending on the volume level, it might be a bit loud. Okay? So let's just see what happens 2 minutes after. Okay, so the interesting thing about that is that you probably heard a series of explosions. And very, very easy to mistake that for missiles, bombs going off, and so on. But what really happened here that was most important is people saw this lovely cloud plume, they'd seen the bright light, they all moved to windows, and what you heard on the video there were all the windows breaking as a result of the shockwave. And that, in fact, injured 1,000 people. And that was something the size of this room. Again, that hits about every year to every few years, something that size. So really, really quite concerning, something that can cause that amount of damage, even though it's small. So it's not just the big stuff that we really want to worry about. So we're very fortunate to have ways that we can start to protect the Earth, to defend the Earth against this particular threat. First line of defense is that we try and observe the sky and we look for these asteroids. So there's an organization called the International Asteroid Warning Network, which is comprised of lots of different space agencies and other organizations with capabilities to observe the sky. So this is actually a telescope belonging to the University of Arizona, the Catalina Sky Survey. We also have satellites that are looking for asteroids. And again, the great thing about satellites is we don't have the atmosphere in between. We can look at things and see them, smaller objects using these kind of technologies. That's not sufficient, because what happens if we detect these objects and we find that one is coming towards the Earth and it has a realistic chance of hitting the Earth? Then we need to do something about it. And I guess for the first time in human history, this is a really major natural disaster that we can actually prevent and stop. Okay, and we can do that using spacecraft. Okay, so the organization that I mentioned at the start, the Space Mission Planning Advisory Group, reports to the United Nations. And this particular group is essentially, we design missions that enable us to stop the asteroid from hitting the Earth. And it can be as simple as launching a spacecraft and hitting the asteroid. Okay, you travel really quickly, hit the asteroid, and you knock it off its trajectory so it misses the Earth. Or it could be that you have a spacecraft that you park next to the asteroid and you maintain the distance. And essentially, we're all familiar with the concept of gravity, because if I jump up, I come back down. Okay, so the Earth is attracting me towards it. You may not be aware that I'm actually attracting the Earth towards me. Okay, so there's a mutual gravitational attraction, and we can use that with this spacecraft. So it exerts a force on the asteroid that's equivalent to a piece of paper resting on the surface. Over a sufficient amount of time, that causes the trajectory to change, so that it misses the Earth. That's all we need to do, is to make it miss the Earth. We don't have to destroy it using Bruce Willis. We can just go in, use one of these spacecraft, and just deflect it, just nudge it so it misses the Earth. Okay, so that's the good news element of my talk. The bad news is the small stuff, we can't see it. We can't see it coming. So my expectation is we see more events like the ones that we saw in Chelyabinsk. Okay, and there probably won't be anything we can do about that. Okay, so on that really happy note, I'll hand over, and you're going to hear even better news now, I think. So.
Brilliant. Okay, well, I'm a little bit depressed now, but I'm going to talk to you about infectious diseases. My name's Rosalind Eggo. I work at the London School of Hygiene and Tropical Medicine, and I'm a mathematical modeler, which means I make computational and mathematical models that explain how diseases spread between people, with the ultimate aim to plan and design interventions to stop them. So, this is a little picture of flu viruses here. And first of all, I'm going to mention the worst flu pandemic in history. So this is the 1918 flu pandemic, and what you're looking at here is weekly deaths from influenza in New York, London, Paris, and Berlin in 1918. And I'll just mark here on the armistice of the First World War. So the 1918 flu pandemic killed 50 to 100 million people, which is many, many more than the First World War. And you can see that infectious diseases are always important, and everybody's collecting data on this. Even during the tail end of the First World War, they're still collecting data because we have to understand these big outbreaks in order to do something about them. The most recent really large outbreak that we all know about is the Ebola outbreak that happened in West Africa, 2013 to 16. 28,000 cases, 11,000 deaths, which is equivalent to about 60% case fatality, although there's some underreporting on the cases and deaths. So about 60% case fatality, which is absolutely huge. If you look at the 1918 flu pandemic, that was around 2 to 4%. So 60% is unheard of. But obviously for the pandemic, that by definition means it spread around the world, and epidemic means that it didn't get everywhere. So that's the Ebola epidemic, but we've had epidemics in human history since the beginning of time. This is just a little plot from London, the plague deaths in London, and you can see from this that the epidemic went up and then it came down again. This is polio in Africa in 2013, and you can see that the epidemic, it went up and then it came down again. And here is the 2009 flu pandemic. Very, very much less severe than the 1918 flu pandemic shown in the EU, and this is deaths from influenza. So again, this epidemic went up and then thankfully came back down again. And so what we're really, really interested in as modelers is how quickly these epidemics start. And the quantity that the first thing we do is try and calculate what's called the reproduction number. So the reproduction number is the average number of secondary cases that each infectious person causes at the start of an epidemic. So when everybody is susceptible and you just have one infectious person, how many secondary cases do they cause? So let's imagine in this scenario that number is 2. Each infectious person causes 2 new cases. Okay, great. So there, in one generation, you go from 1 person, you infect 2, and you had 3. Okay, and then those 2, they go off and find 2 friends, although not friends anymore, and they infect those people. And then those 4 manage to infect 2 people each. You get 8, then you get 16, and then you get 32. So this is the epidemic doubling in every step. If you, and this quantity, this reproduction number, really impacts how quickly the epidemic grows. So what you can see here is the number of days on the X, and then the number of people infected on the Y. And if your reproduction number is 2, your epidemic is still growing down at the bottom. But if your reproduction number is 3 or 4, you can see that the epidemic grows much, much more quickly. And so this is vitally important for planning your interventions and also understanding how much effort you need to put in to control the outbreak. Okay, so this is how an epidemic grows, but if every single time you had one round of infection, everybody managed to double the number of cases, what you see here is in the first, second, third, fourth generation you saw before, but by 33, you've infected the entire world. Okay, well, hang on a minute. That doesn't seem quite right, because that doesn't happen. So what we do is we make models that keep track of the infected people. And yeah, like I said, this doesn't happen, because in reality, as uninfected people become less common, because they've been infected already, it becomes less likely that each infectious person will contact them. So then the infection rate slows down. Okay, and here's an example here. Say that in that second generation, that person there who was infected very early on actually happens to be friends with one of these in the group of 8. So they've already had it, they survived, they recovered, and they're protected. So then when somebody tries to infect them later, they can't. And if this is true for other members of the population, you can see there those blue people represent people who can no longer be infected, but the 15 still try and contact them, then you get a slowdown in the number of new cases. Okay? And so what we do in models is we keep track of all of these people, the susceptibles, the infected, and the recovered. And if it's a severe disease, then the people who've died. And they stay in the recovered or died compartment. So we separate the entire population. They have to be susceptible, they have to be infectious, or they have to be recovered. And they must be one of those states. And they move between those states at these rates, the rate of transmission or the rate of recovery or death. Okay? And this rate of transmission is equal to the number of infectious people, because they're trying to infect people, multiplied by the number of contacts they make on average, multiplied by the proportion of the population that's susceptible, and that is multiplied by the probability of infection on contact. Okay, so the number of infectious people, they try and make contacts, and they make them with susceptible or recovered people or infectious people, and then they have a probability of whether they'll infect those people. And if you make an epidemic curve to represent these transition rates, this is in a population of 5,000. Everybody starts off susceptible apart from one person. We run through time, and then you can see the infectious, the curve is shown in red, starting with one person, and then some people recover or die through time. Okay? And what you can see here is at the point when half of the susceptible people have been infected, then this proportion of the population susceptible is halved, and your rate of transmission to everybody else slows way down. Okay? That's why you get this slowdown and then ultimately the epidemic turnover. The other thing that you might notice about this set of curves is that if you draw a line at 5,000, so everybody's susceptible at the beginning, you'll notice that there's a gap between the recovered and died and the total number of people. So some people don't, it changed my emoji. Some people don't get infected. They never get infected, okay? And that depends on this reproduction number. So the total number of people who are infected in the course of the epidemic is determined by the reproduction number. And what I'm going to show you here is that percent infected in total on the y-axis against the reproduction number on the x-axis. And here are some examples of what we think these reproduction numbers are. So for example, seasonal influenza, around 1.4, 1.5, Ebola, around 2, sometimes 3, pandemic flu, 2.5, SARS, a little bit above 3, and smallpox around 5 to 7. Okay? And then let's see what that final size, this percent infected, looks like. It looks like this. Okay? So you can see here, from 0 to 1, there's no epidemic. Because if the average number of secondary cases caused by each infected person is less than 1, nothing happens. And then it takes off rapidly as it goes over this threshold. And then you see that that line appears to approach 100% at 5. But it doesn't reach 100%. Okay? And then let's take a look. Now I'm zooming in. You see I've put the x-axis to 5, and the y has changed. And these are some examples of infectious diseases like this: pertussis, which is whooping cough, polio, and diphtheria around this point. And has that curve reached 100% yet? No, it still doesn't reach it. And what about if we take it even further? We now change the x-axis from 10 to 15, where we're getting to the upper limit of anything we've ever really seen. Measles is up around 12 to 18, maybe. And then we say, really, it's really not going to reach 100%. This is never going to reach 100%. And this is really good news, because even if you have an epidemic that's really infectious, and in this case, we assume you do nothing about it, still some people are going to make it. Okay? But, and there is always a but there's one infection that could cause a bit of a problem here. And that's the one infection that a lot of modelers like to think about. And that is the zombie infection. Because this one is a little bit more lighthearted. But let's look at why it is that zombie infection might actually wipe out humanity. Okay, so before you saw the susceptible, infectious, or recovered with our rates of transmission and rates of recovery. But what the zombie infection is going to do is it's going to violate some of the rules of this system. And that is, nobody recovers, and although they die, normally when we say they die, that means they like stay in the ground. But so nobody recovers or dies. And then also, the probability of infection on contact, I understand for zombies, that's 1. You never just get a skin wound and move on. Okay, so nobody recovers or dies. You always get infected. And also, in our model, we assume usually that you make contacts randomly with people. But I understand zombies go looking for susceptible people. So that violates that rule. So in which case, the only epidemic that really could infect everyone, according to this theory, is a zombie apocalypse. And that's really good news, because zombies aren't real.
And now for something completely different, I think. So we've heard some fascinating insight from our speakers so far about what risks there might be on our modern world order that might collapse our civilization and end the world as we know it. Well, I want to imagine that's happened. Let's imagine that there has been some kind of apocalyptic event and civilization has collapsed. And let's say that this Faraday lecture theatre that we're in right now has served as some kind of hardened nuclear bunker. And we have survived the end of the world when everyone else has perished. And in about an hour's time, we'll go outside blinking in the early evening light and find the smoking, ruined rubble of London around us. Well, the question that I want to explore is, well, what next? What would you need to know? What would be the most useful science and technology you want to have remembered or have written down somewhere that will enable you to not only survive in the immediate aftermath of this apocalypse, to keep yourself alive, keep yourself healthy, but more importantly, more interestingly than that, how could you go about rebooting civilization from scratch? Could you start from nothing and somehow try to accelerate your way back through history? Could you avoid another dark ages and recover a technological civilization like we have today as quickly as possible after an apocalypse? What could you do if the sort of things that these guys have been talking about has actually happened? And as a scientist, I wanted to explore that. I wanted to think about what you might want to have written down in some kind of quick start manual for civilization, some kind of blueprint for our world that would enable you to see how to make and do everything we just take for granted today. So, in essence, what we're talking about is how might you do this for real? Hands up if you've played Minecraft, if you've enjoyed it. For the older people out there, if you have no idea what this game is, I will guarantee that your kids are crazy for it. I've played Minecraft a single time in my life, and I deleted it off my computer, and I've not allowed myself to go anywhere near it again. It's about the most addictive game you can imagine. And the reason that Minecraft is so wonderful is there's no missions, there's no levels, there's nothing you're supposed to do. It's just a blank, wide-open landscape. You can explore for what you need. You can harvest the natural resources in the world around you, whether that's quarrying stone from a hillside or iron ore from underground, then smelting it with fire to make metal. So how could you do this for real? How could you go about doing Minecraft for real? Well, when I was exploring this project, I looked through, these are blatantly the chapters of the book, what I wrote, the knowledge, and I looked through all these different areas of capability that we rely upon every single day of our lives without really appreciating it. The stuff that's kind of hidden behind the scenes of the modern world, if you like. And something from agriculture and where our food comes from, so we don't starve to death, the basic substances and chemistry that we rely upon, the elements of generating power or medicine. But what I want to talk about is a single example for you now. I've been asked to explain how to reboot civilization in 10 minutes. It turns out that's something of a tall order. So I was going to focus on just a single topic, which is transport. How can you keep the world moving after the apocalypse? By applying your scientific understanding and your knowledge. Because what you would really, really hope that you could prevent happening after an apocalypse, after a fall of civilization, would be our post-apocalyptic society from regressing to a state like this, where you've lost engines, you've lost machinery and mechanisms. You can no longer walk into a car and sit in a comfortable seat and turn a key and drive yourself 50 miles down the road. You have to physically walk yourself to get anywhere. Or if you want to process anything, or mine, or break up the rocks that you've quarried, you have to use your own labor, your own muscles. Humanity for thousands of years has lived with back-breaking labor, and it's the internal combustion engine after the steam engine and this engines and machinery that were invented that's enabled us to relieve ourselves of that labor. So how could you avoid what this chap here has had on? He's looking quite smug for himself, I think. After he's found a car that doesn't work, he's chopped it in half, thrown away the useless front bit with the engine that won't work, found himself some draft animals, like horses or oxen, hitched up to the front and made himself kind of a Mad Max post-apocalyptic chariot out of this useless car, using just the rear axles there. So how could we stop ourselves from regressing to a state like that? How could we keep cars and machinery from running when we no longer have access to crude oil, and the diesel and petrol that we refine from that after the apocalypse. Well, to show you that, I've got a short demo that is all about something called a gasifier stove. Now, here's a gasifier stove that I made myself in about half an hour's time with just some old junk. These are just 2 old tin cans and some very simple tools. And all I've done is taken a big outer tin can, sat on the inside a smaller tin can, and drilled a bunch of holes in the bottom. And to get your gasifier stove to work, you put your wood in the middle, light it, and because of the air holes at the bottom, it draws through a lovely, strong current of oxygen to get a nice, intense combustion inside there, just like any barbecue. But what is unique about this gasifier stove design is you have a second row of holes right at the top. So after the wood has broken down in the heat of its own fire and given off lots of gases and vapors and smoke, which is itself combustible, you then reintroduce oxygen into that mixture of hot gases and burn all of that as well. These stoves are smokeless when they operate and incredibly efficient. Now, I don't get to do this inside and demonstrate anymore. Have you guys heard of the TED lectures? You know, the TED Talks? I was asked out to Vancouver to do a TED Talk last year on the great big red spot of doom. And I sat next to Monica Lewinsky in the makeup chair, ready to go on, very, very nervous, ready to go onto the stage, racking my brains of how to start a conversation with Monica Lewinsky when the only thing you know about her is the one thing you probably should not bring up as a conversational starting gambit. And I also forgot, as I was very nervous, sat in the makeup chair, is just how much hairspray they'd sprayed in my hair. And demonstrating that live on the TED stage, I came that close to setting fire to my own face. So I don't do that anymore. And instead, I've got for you a short video clip of this gasifier stove in operation. Let's get this fired up and see it working. So if you watch your gasifier stove when it's burning, you'll notice the wood itself is not alight. There's a clear gap on top of that wood, and the jets of flame are only coming in at the very top, where the oxygen is mixing with the gases that have been produced by that wood. And because these gasifier stoves are so simple to make yourself, and they're perfectly smokeless when they're in operation, this is exactly the kind of appropriate technology or intermediate technology that's being taught around the developing world by agencies like the United Nations so that a small family living in sub-Saharan Africa can make the most use of the wood they've been able to collect during the day and not breathe in the smoke when they're trying to cook their meal in the evening. The gasifier stoves are smokeless. They're burning the smoke. But what you can also do is take your gasifier stove, scale it up from something the size of an old baked bean can, scale it up to something the size of a dustbin, strap it to the back of a car, and you can run a car using wood as fuel rather than diesel or petrol. That is the gasifier stove on the back where the wood is breaking down and giving off those producer gases, which you pipe over the roof of the car, down onto the bonnet, inject into the engine cylinders, and only then allow it to mix with oxygen and explode usefully to drive your car forward. Now, I will admit, this does look like some kind of crackpot, steampunk, Mad Max contraption, but these things work perfectly well. And in fact, during the Second World War, with all the fuel shortages back then, because we got quite good at blowing up each other's oil refineries, there are over 1 million gasifier-powered cars, 1 million wood-powered cars, driving along the roads of London to keep our society running during that sort of localized apocalypse of the Second World War. I think this is an incredible example of human ingenuity and resourcefulness, and is exactly the sort of level we'd want to try to stop ourselves regressing any further from, so we can start pulling ourselves back up by our own bootstraps after an apocalypse.